I didn't hit the right button. Okay, oh, now I have to start this. I'm just not having, oh no. Okay. Start, it's not my day. Okay, so you can see that you would use a for loop, right? You'd be like, okay, for every way to consider this intermediate node C, I would go to, if I'm trying to figure out how to go from A to B with some number of steps, I consider all the ways to go from A to C with so if I'm trying to take D steps from A to B, then I say, okay, for everything from 1 to D minus 1, I consider the shortest path with the most D steps to C, and then the shortest path with the remaining number of steps from C to B. Okay? So this is a for loop. So you'd say distance from A to B, we assume, okay, currently it's infinite, or actually maybe we have some estimate of it already. So for C, distance, we need more space, distance A to B equals min distance A to B plus min distance A to B in one step. So I'm going to put a 1 here, and this is going to be distance directly. Okay, so this is going to be like the cost of this edge plus distance A to C plus distance C to B. So this is the two ways that you can find this. You can say, okay, either I go directly or I have an intermediate vertex. And if I have an intermediate vertex, I sort of sum over all the ways, over all the choices of vertices and how I go there. Is anybody there? I'm not seeing any. Okay, so, okay, good. How would we do this? I mean, how would you implement this in a cool way? So let's do this because it's called matrix multiplication. Let's write a matrix. Okay. Let's get this right. So let's look here. This is UVWXZ. Okay. So for U, we can go to, this is UVWXZ, and maybe we say, okay, we can go from U to U, from any vertex to itself with cost 0. We can go from U to V with cost 5. We can go from U to W with cost 8. We can go from U to X with cost -4. We cannot go from U to Z in one step. Okay? For V, we can go to U with -2. From V to W, we cannot go in one step. So it's infinite. From V to X, we cannot go in one step, so that's infinite. From V to Z, where is Z? We cannot go in one step, so that's infinite. From W to U, we cannot go in one step. From W to V, we can go with -3. From W to X, we can go with 9. And from W to Z, we cannot go in one step. X, I should have written this up before. X, we can go to Z with 2. X, we can go to V with 7. And this is infinite for the rest of them. And finally, for Z, we can go to U and W with 6 and 7. Z, and that's the only places we can go in one step. Okay, so we have this matrix. Now, how can we work out, thinking about that for loop, how can we work out easily what the shortest paths are using 2 steps? Okay, so I'm going to insist that now I want the lengths, the distances using exactly 2 steps. So what we can do is write the same matrix minus 4, infinite. This is a 0. Okay, so we write this out. Now, we think about, so if we're going from somewhere to somewhere else in 2 steps, we go from the somewhere to an intermediate vertex, and then, so if we're going from W to X in 2 steps, okay, then we look at W to X. So we're going to look at all of the ways to go from W to somewhere. Well, let's say from W to Z. Yeah, because you can't normally get from W to Z. Just a double for loop. Sort of, but this is a nicer way to do it, because this is going to tie back into matrix multiplication, and we've seen lots of tricks for speeding up matrix multiplication. It's not really matrix multiplication, but you'll see why it sort of is. Right? So this is all of the ways to get from W to somewhere. And then what are the ways to get from somewhere to X, to Z? Right? They're here. Oh no, Z is kind of boring, because Z there's only one that you can get to. So where else? Yeah, let's say W to U, okay? So we're trying to get from W to U. So these are all the costs of getting from somewhere to U, okay? So how can we talk about the cost of getting from W to U in 2 steps? Well, if we try to go from W to U in 1 step and then go from U to U, it will be cost infinity. So, and I'm assuming you're allowed to stay at a vertex for 1 step, because that's why I put the zeros in. I forget if in the book it's infinite, or if you're not allowed to do that. I'm saying you're allowed to do that. Okay, so it's going to be infinite plus 0. So that's if I tried to go from W straight to U and then sit at U for the second step. Okay, it's not exactly 2 steps. It is if you count sitting at U as a step. If I go from W to V, right? So this is this and this. I sum this, and this is infinite. Okay. But then I take -3 and -2. Okay, that's a bit weird. But I can go from W to V in cost -3. And then I can go from V to U in cost -2. So I can go from U to, I can go from W to U with cost at most -5, right? Because I can go from W to U, I will go to V, yeah, -3 and then -2, it's -5. Okay, then I have a 0. I can go from W to W, I can just stay at W. And then I can go from W to U with cost infinity. So it's 0 plus infinite. And then I can go from W to X and go from X to U, and that's cost 9 plus infinity. And then I can go from W to Z and Z to U, and that's infinity plus 6. Okay, so that's also kind of boring. But what do I put in the step? Now, notice that this is not what we do for matrix multiplication. For matrix multiplication, these pluses are times. They're a dot, right? Because you take these two components. If I'm working across here, if I'm working across this row and down this row, then for each pair of components, for each pair of entries, I'm multiplying them, and then I add all of this stuff. But now, if I want the shortest path in 2 steps from W to U, I'm going to take the sum of, for each way to go from W to somewhere and then somewhere to U, I'm going to take the sum of those 2 pieces, add them. That's the cost of that path. And then I'm going to take the min over all of these things, right? So it's just, instead of taking where I normally take plus, where I normally take multiplication, I take plus, and where I take plus, I'm taking min, right? Do people see that? Or do we want to see some more? Maybe. Maybe we want to do another one? Another row? So let's consider going from X, so okay, and then we take a min of all of these things, and that tells us that the cost of going from W to U in 2 steps, allowing yourself to stand in the same place, so actually it's at most 2 steps, is going to be, well, in this case, all of the rest of these things are going to be infinite, and this is going to be -5. Okay? So let's consider X. Let's consider how can we do this? Yeah, okay. Let's consider U to V. I wouldn't be opposed to more. Okay, good, because we're going to do more. Let's do U to V, because that's an interesting one. So U to V, we're going to do, but you see the idea is it's just like matrix multiplication, but here instead of a sum, instead of a big sigma, I'm writing min, and in each of these, instead of a multiplication, I'm writing a sum, an addition. Okay, so let's say we're going to do U to V. The T is doing me good. I may stop for another drink of tea. Okay, I didn't need to erase that one. Okay, let's do u to v. Okay, so we can go from u to v, and then well, we can go from u to v and oh no, this goes u to u, okay? U goes to u, so u sits, we don't move. For the first step, we don't move. U goes to u, and then on the second step, u goes to v, okay? So that is 0 plus 5. Okay, and then we can go u goes to w, which is 8, plus u goes to u goes to u goes to oh, then this one is, oh, this is the, sorry, I forgot one. U goes to u, then u goes to v. U goes to v is 5, and then v goes to v, and v goes to v is 0. So what can we do in two sets? Like u can go to v and sit here, and sort of you go 1, 2, or you can go 1, 2, doesn't matter. So now we're considering going to w with 1, 2. So u goes to w, u goes to w is an 8, and then w goes to v, it's a minus 3. So I'm going to minus 3. Okay, so that's 5. So these two are actually the same, but we don't care because we don't actually. So okay, now u goes to x, and so if we were multiplying these things, you see I would be doing this, and it would be minus 4 times 7, but now it's minus 4 plus 7. And then finally it's infinite and infinite. Infinite, not 8. So now if I take the min over these, it's going to be this one. It's going to be 3. Okay? So the shortest path to get from u to v in at most 2 steps has length 3. Okay? So you can do a matrix, basically a matrix multiplication, where we can do the multiplication we know and love, and it's like cubic time. Okay? And this is simple and easy to remember, and maybe, I don't know, can you? I don't think. I wouldn't bet my life that you can do speedups like Strasson's algorithm, because that's using the fact that you can add 2 matrices, and maybe that's going to change. Probably that's going to change if instead of addition you're working with min and so this is called min plus, I think. Yeah, so the normal one, the normal matrix multiplication is like addition multiplication, and this is min plus. So you can see, so how do you, if you want to work everything out in, for 2 steps, it's going to take you like cubic, it's cubic time, which is like, oh, that's horrible. But cubic in the number of vertices. So, okay, how does that help? Like, if you want to find the shortest path, I told you, well, the shortest path has to have length at most n. So now you're going to get something that's quartic, right? That's n to the 4, which is horrible. How do you get this actually to work in practice? You use this trick called repeated squaring. So on the midterm, there was a question about counting paths. So this, you can also do these kinds of tricks for reachability, because you take the adjacency, instead of a cost matrix, you take the adjacency matrix and you multiply and you square that. And this is going to tell you if you can get from some vertex to some vertex in exactly this many steps, or if you sum them together in at most this many steps. I will probably put this in the lecture notes when I actually get the lecture notes done. If I actually get the lecture notes done. So here, you don't want to do if this is matrix M, then to compute the shortest paths of length 2, you take m times m. To compute the shortest paths of length 3 or less, it's m times m times m. Times being this weird min plus thing. And then for 4, it's m times m times m times m. But you can get that just by doing m times m and then squaring that. Right? So it's actually just 3 multiplications. And then if you want, so you can actually work out if you want, it doesn't matter, because if you go over, then if the shortest path has length 6, then if you're computing the shortest path of length at most 8 or 16 or something like that, it doesn't matter. It's still just going to be this, if it's at most 16, it's still going to give you the length of the shortest path of 6. Okay? So you just do repeated squaring, and how many times do you have to do that? You have to do it a logarithmic number of times, right? Because the shortest path, you know, as long as there are no negative weight cycles, the shortest path is always, between any two vertices, is always of length at most n. Therefore, if you're sort of doubling the lengths, the maximum lengths each time, you have to do like log n squares. So ultimately, this is O of n cubed log n, which is like not too bad, sort of. No, it is. It's pretty bad. On a big graph, cubic is horrible. So, okay, I trust like people who are more awake than I am. Bellman-Ford is not hard, right? You're just going to say, okay, at each round, everybody for every edge, we check to see if the distance from the starting point to the one endpoint of the edge plus the cost of the edge is less than the distance to the other endpoint. If so, we update that, and then you just have to repeat that n times. Okay, so Bellman-Ford is easy. This is a little bit cool. You know, you see, okay, that's neat. So like all of this stuff we have that's optimized, not all of it, but maybe some of it, that's optimized for matrix multiplication, you can use here. Not all of it. Now let's, wow, we're actually getting through this really quickly. Maybe not. Okay, so Floyd-Warshall, this one I have to, so this is basically the same idea, but not exactly. So this, you can get cubic time without this log. Okay, but it's very similar. It's still, this is matrix multiplication. Now it's going to be dynamic programming. So before, I was talking about sort of distances. Now we're going to be talking, I was also talking about intermediate vertices. But now we're going to be considering intermediate vertices, and so one of the reasons I'm so sad, the solutions to midterm 2 are up, and I stayed up late doing those.